Last week, we looked into CCTV headquarters design issues and various problems caused by design. Also, briefly learned about the diagrid system, foundation, basement, diagrid frame system, and butterfly plates used to solve these problems. This week, we will have a more in-depth understanding of CCTV headquarters filed left foundation. CCTV is located in the Central Business District of Beijing Chaoyang District, China. It is located in the alluvial layer of the Yongding River and in the middle and lower stream of diluvium pan. It has 12 layers of pebbles, gravel, silt, and sand buried under 160 meters of bedrock. The depth of the foundation stone is about 20 meters, and the fourth major layer includes the viscous soil and silt layer. The support of the soil around the main tower of CCTV is not sufficient to remain within the allowable subsidence limit while supporting the total load from the upper structure. Pile foundation is the type of deep foundation. Now the question is, why pile foundations are used? When the structural load is less or moderate, it's economical to use shallow foundation. But where the structures constructed are large and heavy, the underlying weak layer of soil will not able to bear these heavy loads. It causes settlement and damages to the structures. Pile foundation is the solution here. It transposes the heavy loads through the underlying weak soil to the lower level of hard and strong subsoil.
In most modern heavy buildings, the structure's columns are provided with combined footing as a whole. A single reinforced concrete slab is made for each and every column. These footings are called raft or mat types, and they spread the load evenly imposed by a number of columns or walls on the soil. This type of footing is adopted to avoid deep foundations, which would otherwise go around 60 to 200 feet deep. In an area with expansive soil, the raft foundation is a boon that lessens the chances of differential settlement.
Like the Burj Khalifa and CCTV, use a combination of raft foundation and filed, which forms a combination of shallow and deep foundation. In situations where a raft foundation alone does not satisfy the design requirements, it may be possible to enhance the performance of the raft by addition of piles. The use of a limited number of piles strategically located may improve both the ultimate load capacity, the settlement, and the differential settlement performance of the raft. The following is each graph of load settlements of raft, pile, and piled raft foundation. Piled raft foundation utilized pile support for control of settlements with piles providing most of the stiffness at serviceability load, and the raft elements providing additional capacity and ultimate loading. In conclusion, it can be confirmed that when a pile is combined rather than a foundation with only a raft, it is possible to reduce subsidence and increase stiffness compared to the same load through interaction with its soils. Since the foundation load was very large, the foundation of the stake was most stable for the tower. Load tests were conducted on two types of stake. There are TPA, a stake with an effective length of 52 meters with 12 layers as the support layer, and TPB, and a stake with an effective length of 34 meters with 9 layers as the support layer. All of them had a diameter of 12 meters. As a result of the experiment, the compression amount of TPA is 21 millimeters, which is 88% of the pile drop and 149 mm in the case of TPB, which is 78% of the pile drop amount. It shows that the longer the length of the stake, the higher the compression amount. The lateral frictional resistance within the range of 50 meters at the pile end of TPA cannot be effectively mobilized. TPB was superior to TPA in terms of strength, pile top deformation, and pile body compression, and was more cost-effective. Therefore, the ninth floor was selected as a filler and supporting layer of TPB. Also, grouting was done to strengthen the support of the ground. Due to the cantilever and the tilted tower, the load on the superstructure has a high eccentricity. Each has a larger load on the inside of the tower and a smaller load on the outside. The pile arrangement followed the arrangement of various rigidity of unevenness with different densities. From the center of load to the periphery, the number of piles and pile arrangement gradually decreases. Therefore, the joint force action point of the pile approaches the action point of the upper load, and the error becomes less than 1.5%. The maximum reaction force of the pile in Tower 1 is 12,000 kN in the southeast of the tower, and the minimum is 5,260 kN in the northwest. Tower 2 is 10,800 kN in the northwest and 5,260 kN in the southeast. This figure shows the flat arrangement of the pile. There are 277 piles for Tower 1 and 288 piles for Tower 2. Rafts are also designed in various thickness to preventing bending, shear, and perforation due to uneven load on the top. In the case of left shear, it was calculated according to the dangerous cross-section of the raft, showing that the most disadvantaged cross-section of the shear is located outside the cores of the two towers, and the pile is closest to them. Therefore, anti-shear reinforcement is installed at the core edge of the two towers, which is the same as the core filler embedded in the raft. Therefore, the maximum thickness of the raft is 7 meters for Tower 1, 6 meters for Tower 2, and the minimum thickness is 4.5 meters. We have now completed the third week of presentations. In the first and second weeks, basic information about the building was presented. This week we gave a presentation on site analysis and how a foundation combining files and raft was able to support the Cctv headquarters. Next week, we will present the building settlements and how the columns and beams are constructed on this solid foundation and how it was able to withstand the load of this unique type of building. Thank you for your attention.